So good afternoon. This is session 4 of partial differential equation, and in this session we will solve into Cauchy problem, that is to find out the integral surface passing through a given curve. That means we are given a curve and need to find out an integral surface. So what I'm talking about, let's see. So the Cauchy problem. Now see. Let's say I'm given a problem. So let me take one first problem and then you will understand for sure. So that is, what's wrong with this PC, friend? The integral surface. So find the integral surface of PD x times y square plus z times p minus x square plus z times y cube equals x square minus y square times z. So find the integral surface of PD which contains the straight line which contains the straight line x plus y equals 0 and z is 5. That means earlier while solving a PD, we used to get an arbitrary function, right? We used to get an arbitrary function. Let's say you got this one. Fine. So this here it was an arbitrary function, but right in Cauchy's problem, basically this 5 won't be there and there will be no constants. It will be completely a surface. It will be completely a surface. The solution of that PD will be completely a surface and it will contain this curve. Okay, so we have to parameterize this curve and then with the help of this curve, we will remove those arbitrary constants. Okay, so that's the main problem. It's called Cauchy problem. The process is exactly same as the Lagrange method. Okay, so solution is quite simple. Watch out. So 1 times x square plus z into q equals x square minus y square times z. So by Lagrange method, let's say you got this dx over x times y square plus z equals dy over it is minus, so minus y times x square plus z equal to dz upon x square minus y square times z. You have to play with the same constants again and try to make things, cancel the things, or you can do whatever you want. Okay, so the first thing that I generally do is I just multiply and check if this works or not. If this doesn't work, I'll try to find out new constant. Okay, let us see if it works. I think it will work. X square, y square, x square, z square. Yeah, it should work. Let's see. So now this part will give me, let's multiply. So x dx plus y dy plus z dz upon, now watch out, so it will be x square y square and plus x square z, and then it will be minus y square x square and minus y square z, and here it will be plus z square x square. Am I missing something? Because it should be x square minus y square. What am I missing? Yeah, I made a mistake here. Z x square, yeah, that is perfect. Something is wrong here. What? Because this is getting cancelled, this is getting cancelled. Let me check one more. So it will be y square, y square x square, that's fine. Y square z, okay, plus z square x square, and then minus z square y square. So this z is playing the role. What is wrong? Oh, in fact, this z is extra. So we don't need this z. Don't need this z only. Now it is perfectly fine. So it will be z square Going to be z square. Simply z square and minus zy square. This is perfect. So this will get cancelled. Just a moment. And I can't cancel this because these two signs are same. So what if I do this? Minus, it will be plus. Now let's see. Zy square, yeah, it is getting cancelled with this part, and zx square will get cancelled. This is minus, not plus. Okay, because I've subtracted. So it will be absolutely minus. So this will get cancelled and this will get cancelled. Now you can consider any two pairs. Okay, you can consider any two pair and say this part is going to be 0. So x times y square plus z equals x dx plus y dy minus dz upon this entire quantity is 0. So now I'll be getting this numerator thing, x dx plus y dy minus dz equal to 0. And now I'll simply integrate. So x dx plus y dy minus integral over dz equals integral 0. So this part gives me x square by 2 plus y square by 2 minus z equal to c1 dash. Now just take this 2 here, so I'll be getting x square plus y square minus 2z equal to 2 c1 dash. I'm calling simply c1. Here I write it down, c1 equal to 2 c1 dash. So this is my equation 1. I found this, and now the next goal will be to find out the next set of constants. So let me see again what I have here. Yeah. So now consider again. So you again consider the same thing. So dx upon, what was that? X times y square plus z equal to dy upon b minus y times x square plus z equal to dz upon x square minus y square upon z. Now let me see if I can play any role. So dx upon x times y square plus z equal to now what role can I play? Just a moment, it will be again a trial. So let me see if it works. What if I take this x there? See, in fact, it is clearly visible. Take this x there, take this y there, and take this z there. We have x square, y square, and z. So there is no need for a calculation. It will be simply resolved in single step. Take this x there, take this y there, and take this z also there. Okay. So I have taken all of them. No. Let's see whether we have to cancel or do what we need. So it will be y square plus z, and here it is minus already. So it will be minus x square minus z, and here it will be x square minus y square. So we need to add this one. This is already added, so plus and plus. I think all of them are getting cancelled now. Yeah, lucky. So this implies this take numerator. This entire quantity is 0. So this numerator forces the numerator to be 0. All right. So now just integrate. So 1 upon x dx plus 1 upon y dy and plus 1 upon z dz equals integral 0. So this part will give me log x plus log y plus log z equals, instead I'll write down this log c1. C1 is done, c2. So take all of them together. So it will be log of x, y, z equals log c2. And from here I get x, y, z equal to c2. All right. Now from here, this was the earlier problem. Okay. So now, what's next in Cauchy problem? So you are given the surface. Okay. The surface is what they have given. The curve they have given is x plus y equal to 0 and z is equal to 1. So let us assume that they are on a surface gamma, and where z is 1 I'll be putting y equal to t. Okay, so just to parameterize the curve, nothing. I'm just parameterizing. Okay, so instead say parameterizing. Whatever curve we give, just parameterize first. So parameterizing x plus y equal to 0, z equal to 0. So just put y equal to some t, and then z is 1, y is t, so x will be from here minus t. So you have parameterized the curve. Okay, now since you can write down phi of x, y, z equal to, yeah, phi of c1 equal to c2, I'm writing x square plus y square minus 2z. So x square plus y square minus 2z. You can write down this one, or you can also write down this one. So, but I'll suggest you write down which seems to be more convenient and easy to calculate, because you will be substituting all these values in this to remove this arbitrary function phi. Okay, because we need a surface, so not an arbitrary function. So instead, what you can do, you just take this one. In fact, it's quite simple. Or this one, x square plus y square will be t square plus t square minus 2. Okay, so I'll take this one. So since x is your minus t, y is your t, and z is equal to 1. So substitute in this equation. So you get what? Phi of x minus t, t, and 1. So it will be basically minus t square, and it will be equal to what is x is t square, and then plus y is also t square, and minus 2. So that will give you what? 2t square minus 2. So phi of minus t square equal to 2t square minus 2. Now you have to make it into a single variable. So put minus of t square equal to some omega. So therefore, from here, t square will be minus omega. So that means I'll be getting phi of omega equal to minus 2 times omega minus 2. Okay, because t square is minus omega now. So you're getting phi of omega to be minus 2 omega minus 2. And now I'm using this equation. Okay, so instead of omega, put this value, and then equate those two functions. Therefore, phi of x, y, and z will be equal to what? Minus 2 times x, y, z, and minus 2. But since phi of x, y, z is what? X square plus y square minus 2 z. Okay, so just simply equate these two. Call this 1 and call this 2. Okay, equate them. I think we have used so it is 2 and 3. Okay, so equating 2 and 3, you get the equation. Equating 2 and 3, just equate them. So you get x square plus y square minus 2z equal to minus 2xyz minus 2. Let's take all of them there. So x square plus y square minus 2z plus 2xyz plus 2 equal to 0. This is the required surface. And such problems are quite often in CSIR, NET examination, or GATE. Okay, so make sure that you have ample practice to solve all of them. Okay, now there is one more method to solve this problem. Okay, from here onwards. Okay, from here onwards, you can even solve this by another method. Okay, so from here, so this is method 1. I'll write down. There is one more method. If you don't like this big calculation, there is one more method which has even more calculation, but it may look easy. Method 2. So once you parameterize the curve, this is your minus t, t, or 1. You can put any one t, so doesn't matter. Even if you put x equal to t and y equal to minus t, still you will end up with the same surface. So you don't have to worry about it. Now let's see. So what I have got. What is C1, by the way? And to find out, C1 was x square plus y square minus 2z. X square plus y square minus 2z. So x square plus y square minus 2z. And C2 was just simply xyz. So instead of writing phi as a function of C1 and C2, you simply substitute these values and even in fact remove this C1 and C2 by some calculation. Okay, so therefore C1 will be what? It will be t square plus t square minus 2, and C2 will be what? It will be simply minus t square, simply minus t square, right? Because x, y, z will be minus t square. So what role can I play? Okay. What role can I play to remove this C1 and C2? Okay, or find out a relation between C1 and C2. So I'll write down the hint. Okay. So find a relation between C1 and C2. Free of t. Okay, so our hint is to find out the relation between C1 and C2 free of t. So that means I can say this C1 is 2t square minus 2 and C2 is minus t square, correct? So if I multiply by 2 and add them, so this gets cancelled. So the relation that I'm getting is C1 plus 2C2 equal to minus 2. Now in this, just substitute what are C1 and C2 and you are done. Just substitute. What is C1 by the way? C1 was x square plus y square minus 2z plus 2 times C2. C2 is what? XYZ. So XYZ and take this one here. Plus 2 equal to 0. You haven't got the same surface. Okay, so there are two methods. In fact, this one is quite easy, but not every time you can find out the relation between C1 and C2. So that's why I've given one more method, and this method will be is universal. In fact, you can find out you can use this method to solve any particular problem, but solving this method or solving the problem by this method will invite some troubles later on. If you don't get a relation between C1 and C2, then what? Okay, so it is better to go by this method, but still you can work with this, no issues. Okay, so I hope you got the idea to find out an integral surface. So I'll give one more problem from GATE examination. You can try this. So this is a problem from GATE. I don't remember the year exactly, but while solving the paper, I have seen this one. The integral surface satisfying yp plus xq equals to x square plus y square and passing through x equals to 1 minus t, y equals 1 plus t, and z equals 1 plus t square. So they have already parameterized. T is the parameter. Okay, they had already parameterized. So now the options are option A. Option B is z equal to square by 16 times square plus 3 times that is what square plus 1 by 8 times okay. So there are four options. They're asking this. See, one method is to check by substitution. Just put 1 minus t and y as 1 plus t and see if you get 1 plus t square. Okay, that is one method, but it is time consuming. You can't simply solve all of them together, and you don't have that much time in GATE because GATE exam is only for 3 hours. Okay, if it is for a whole week, you can try. So let's solve. So yp plus xq, uh, yp plus xq equals x square plus y square. So you can apply your Lagrange method. So by Lagrange method, you will get dx over y equal to dy over x equal to dz over x square plus y square. Now, from here, things are quite clear. First, I'll consider first two pairs. First, consider first two, right? This half of the thing will be simplified here. This is variable separable, so just take this x dy equal to y dy. Now simply integrate them, so you get x square over 2 equals y over 2, y square over 2 plus c1 by 2. So this implies x square minus y square equal to c1. Well, I got one part. Now, finding the first part, what we can do is, yes, again, let's write down also dx over y equals dy over x equals dz over x square plus y square. Even a novice can tell me that I have to do this y square x square and subtract, right? It will be cancelled. So can I do this? Y dx plus x dy minus dz. Okay. Hold upon, I'm writing in red because it will get cancelled. So see here, it will be y square plus x square minus x square minus y square. So this entire part becomes 0. And this forces our numerator to be 0. So it will be y dx plus x dy minus dz equals 0. So you can't integrate simply, so just write down there dxy and minus dz equal to 0, and now integrate. So you get xy minus dz equal to some c2. So you got this thing again. So therefore, you have two choices from here. Okay, which one is to use? So you have phi of. I'll write down in this manner because I won't go for finding a relation between C1 and C2. If you ask me why, I'll simply say I don't like square minus y square. Square minus y square. Now, since let gamma be the surface, parameterized form of this, that's a parameterized form of this given curve. So what is given? X is what? 1 minus t, 1 plus t, 1 plus t square. So x is 1 minus t, and this is 1 plus t, and this is 1 plus t square. So now we just need to find a relation between them. So, or you can write down even phi of x square minus y square equal to xy minus z. I'll consider this one while solving because x square minus y square. So these two are nice equations. So therefore, phi of x is 1 minus t square minus 1 plus t square, and x is again 1 minus t into 1 plus t, and then minus z square. That means 1 plus t square. Yeah, happy? Let's go. Oh, it's not z square, by the way, so we don't have to worry. Just leave it. No. So therefore, phi of, if it's found, then a minus b square minus a plus b square. That simply gives me minus 2 times 2 into 2 from here, 2 from here. So 4t simply. Okay, it will be equal to, this is again 1 minus t square, 1 plus t square. So 1 and 1 will get cancelled. I'll simply get minus 2t square. Okay, you can verify and check it. Okay. I have polished binomial expansion more. So it will be cancelling minus 2t square there. That's fine. And now the demand has come to put this some value, because I convert into some variable and then I'll just introduce x square minus a square, and then I'll compare these two. Okay, the way I have done earlier. So let minus 4t equal to some omega. So from here write down what is t. So t will be equal to minus omega by 4. So therefore phi of t, phi of omega, will be equals to minus 2 times t square. That means minus omega over 4 square, and it will make it omega square by 8. Okay, and that to minus. Okay, so therefore phi of, instead of omega, I'll put x square minus y square, because I need to find out what is x square minus square so that I can equate these two surfaces. I have phi of x square minus y square. From here, I'll just substitute. So phi of x square minus y square from here will give me minus x square minus y square upon 8. But I also know that phi of x square minus y square is xy minus z. So this is your equation 2 and this is equation 3. So just equate 2 and 3. So equate 2 and 3. And see, nicely you get, yep, so xy minus z equals minus of x square minus y square upon 8. So from here, just substitute in the form of z, so it will be xy and it will be plus. So 1 upon 8 times x square minus y square. Okay, so plus 1 by 8 and that is square. So plus 1 by 8 square. So D is the correct option. Alright, so I hope you followed. What is the Cauchy problem? Cauchy problem. Now I'll solve one more. Instead, you try and I'll continue. Okay, so you got one more problem. This you can try. Okay, let me know. So let me check one problem again. So problem number 3, and this is the last problem for Cauchy. And in the next session of PD, we will continue with something different. Okay, plus, so z minus 2x square times q equals to is by y equal to 2 times x minus yz passing through I'm already parameterizing. Instead, let me say this is passing through x equal to 1, y equal to 0, and z equal to some t. Fine. So you can pause the video and start the solution. See if you get it. The problem is quite easy. I'm giving it. So at the same time, I'll try for you, but instead you should solve on your own. Lagrange method, dx upon 2xy minus 1 equals dy upon z minus 2x square equal to dz upon 2 times x minus yz. Now let's see which game we can play. So here first I'll do what I generally do. I'll play with x. If this works, then good. If not, we will try another constant. Constant in the sense, this time function we have. So just check here that this works 2x square y minus x plus yz minus 2x square y and plus it is 2x only. 2zx. No, I don't need 2x. No, zx. Okay, in fact, I don't need this. And I don't need this 2 even. Okay, I'll shift this half in the numerator. And see, I'll be getting x minus yz. And see how lucky I was. All of them got cancelled. So this entire quantity now became, that is, dx upon 2xy minus 1 equals dy upon z minus 2x square equal to dz upon x minus yz is now equal to simply what I multiplied x dx plus y dy minus plus half of z. This is what I had done. And upon I know that this denominator is completely 0. Okay, so you can consider any part and say x dx plus y dy plus half z, or it is not dz in fact, equal to 0. And now integrate it. So you get x square by 2 plus y square by 2 plus z by 2 equal to some c1 by 2. So from here you get x square plus y square plus z equal to c1. So I'll call it 1. Yes. Now go for the next one. Oh god. Consider the another pair now. So we can say you consider what is there, dx upon 2xy minus 1 equals dy upon z minus 2x square equals to dz upon 2 times x minus y. Now let's find new constants. Can So what we can do is 2xy, if I multiply by z, just remember this is a trial z. So 2xyz. Now from here I'm getting 2, yeah, here it is yz, this is 2. So I multiply by x now, just to get x, and let's see what happens. So in the denominator I'll be getting 2xyz minus z, and just add this one. So I'll be getting 2x square and then minus 2xyz. And now let's see what to do with this thing. I think this, if we add simply, we are done. Watch out. Okay, so we just have to add in fact. So the method is quite powerful. So this implies, let's say, dx upon 2xy minus 1 equals dy upon z minus 2x square equal to dz upon 2 times x minus yz equals, what I've got is z dx plus x dz and minus dy. No, not minus, plus. Upon this entire quantity becomes 0. So now from here you can conclude that z dx plus x dz and plus dy is 0. So now you can integrate and say, you can't, because here it is z dx. So instead you move one more step and write down like this. It's the same thing. And now from here you get xz plus y equal to 0. So now you have got phi of xz plus y equal to, what I have is x square plus y square plus z. So x square plus y square plus z. Now since gamma is what? X is 1, y is 0 and z is t. So we're lucky we are, because it is ultimately giving me x is 1, z is t, and y is already 0. So phi of t, I simply got a 1 plus t. So phi of, instead of this t, you don't need to put anything else. Simply take this phi of xz plus y. It will be what? 1 plus xz plus y. Now phi of xz plus y is what? Just equate this one. So x square plus y square plus z. So now just take this one here. So you get x square plus y square plus z minus xz minus y minus 1 equal to 0. Is the required integral surface. Okay. So I hope you got the Cauchy problem. But again, let me make it very clear, because this is Cauchy problem for linear. Okay, this Cauchy problem is for linear PDE. Okay, I'll get back again in my next session with the Cauchy problem for non-linear PDE when we complete Cauchy problem, when we complete non-linear PDE by solving by Charpy method. Okay, so Thanks for watching. That's all for this session. We'll continue in section 4.